Hello everyone. In this video, I'll discuss an important interview question: how to implement a high performance circular shifter in digital designs. Let's get started. First, the basics. A hardware shifter is a combinational digital logic circuit used to move bits within a binary number, either left or right, by a specific number of positions. In modern digital design, we can find these circuits used extensively throughout the processor data paths. They are used in arithmetic operations like fast multiplying or dividing by power of 2, address calculations, data alignment, and bitwise manipulations. One of the popular choices for high performance data shifter is the cascade barrel shifter. Now let's understand the cascade barrel shifter design. The primary advantage of the cascade barrel shifter is that it can shift or rotate data by any specific number of bits without relying on sequential elements like flip-flops. It is purely combinational circuit. This means that it can rotate or shift data by n bits just in a single clock cycle. Because it is incredibly fast and gets the job done in one clock cycle, it is preferred shifter design in modern microprocessors. A barrel shifter circuit relies on cascading chain of multiplexer stages. Each stage in the cascade conditionally shifts the data by a power of 2 amount, for example, 1 bit, 2 bit, 4 bit, and so on. And the final shift is determined by combining the control signals across the stages. After the theory, let's see how do we actually describe this in hardware. Here is a generic Verilog code for a cascade barrel shifter. Let's look at an example now. Here is a 4-bit barrel shifter that performs a circular right shift, also known as rotate right operation. For a 4-bit input, the data can be rotated by 0, 1, 2, or 3-bit positions. To represent these four possible shift amounts, we need 2-bit shift control signal, which we'll call shift bit 1 and shift bit 0. This barrel shifter is implemented using two stages of multiplexer, each stage responsible for a power of 2 shift amount. Stage 1 is controlled by shift bit 1. When shift bit 1 is 0, the data passes through unchanged. When shift bit 1 is 1, the data is rotated right by 2-bit positions, which corresponds to 2 to the power 1. Stage 0 is controlled by shift bit 0. When shift bit 0 is 0, the data passes through unchanged. When shift bit 0 is 1, the data is rotated right by 1 bit position, which corresponds to 2 to the power 0. Each stage consists of 4 2 to 1 multiplexer, 1 for each output bit. In stage 1, all 4 multiplexers use shift bit 1 as their select signal. Depending on the value of this select signal, the multiplexers either pass the input directly or output the version of the input rotated right by 2 positions. The output of stage 1 becomes the input of stage 0. Similarly, stage 0 consists of 4 2 to 1 multiplexer where shift bit 0 works as the select signal. When shift bit 0 is asserted, the data from stage 1 is rotated right by one additional position. Otherwise, it passes through unchanged. By combining the effects of these two stages, this barrel shifter circuit can perform rotate right operation from 0 to 3 positions. The truth table here summarizes the output for each possible shift value. Now let's extend the same concept to a 8-bit barrel shifter. An 8-bit barrel shifter can perform a circular right or rotate right operation by 0 to 7-bit positions. Therefore, we need 3-bit shift control signal, which we can call shift bit 2, shift bit 1, and shift bit 0. Just like 4-bit barrel shifter, the design is built using multiple stages of multiplexers, where each stage corresponds to a power of 2 shift amount. Stage 2 is controlled by shift bit 2 and performs a rotate right by 4 positions when enabled. Stage 1 is controlled by shift bit 1 and performs a rotate right by 2 positions when enabled. And stage 0 is controlled by shift bit 0. This performs a rotate right by 1 position when it is enabled. Each stage consists of 8 2 to 1 multiplexers, one for each output bit. The outputs of one stage feeds the input to the next stage, allowing the shift to accumulate. By enabling different combination of stages, any rotate right operation from 0 to 7 positions can be achieved. For example, if the shift control value is 101, stage 2 rotates the data by 4 positions. In stage 1, the shift bit is 0, so the output is same as input, and stage 0 rotates the data by 1 position. This results in a total rotate right operation of 4 plus 1, 5. So the input is rotated by 5 positions. The key point is that even though the shifter supports 8 different shift amounts, it requires only 3 stages of multiplexers, which is equal to log base 2 of 8. This logarithmic structure is what makes the barrel shifters fast and efficient for implementing variable shift operations. Thus, we see that a barrel shifter achieves any shift amount using only log base 2 of n stages of multiplexer, where n is the data width. This logarithmic structure allows the barrel shifters to perform a variable shift operation in a single clock cycle, while keeping the logic depth relatively small. Barrel shifters consist of repeated mux stages. This makes it easy to design and verify. Designers prefer this structure because it is highly regular, synthesizes well, and it scales efficiently as the data width grows. This is all for this video. I hope you find it helpful.